Hello and welcome to this lecture on mechanical design. We will continue our discussion of the mechanical behavior of materials. And in the last few segments, we've learned about strength and cold work. We've learned about the concepts of toughness and resilience and the difference between these two. And today we're going to talk more about impact properties. So if we consider impact is very important in applications where we have high strain rates as a result of interaction between a force and the product that we're designing. For example, in a car crash, the strain rate will be very high, and therefore the properties will depend on this strain rate that we are considering. So to measure the ability of the material to resist impact, there is a standard test that has been developed by a scientist. His name is Charpy. He's a French scientist. And this test is rather simple. It actually measures the amount of energy absorbed by the material before it fractures. And in order for us to get this absorption amount, we need to standardize the test. So the American Society for Testing Materials, ASTM, has standardized the size of the sample and the way that the test is performed. So the specimen is struck by a pendulum, as I'll show you in a minute. And the energy absorbed is called impact value and is computed just from the heights of the pendulum before and after the impact. And we'll get into that in a minute. So the American Society of Testing Materials, the ASTM standard A370, shows that the sample is 10 millimeter by 10 millimeter by 55 millimeters, so it's 1 by 1 centimeter in cross section, and it's long. It's 5.5 centimeters, and the sample is notched in the middle. So there's a notch right here, and this is a detail of the notch at 45 degrees, so that the notch concentrates the stress during the impact test and produces localized fracture to compare one material to another. So the sample is shown here, and this is the notch that we were discussing with a standardized 45-degree angle. And then the test is performed with a pendulum, and the pendulum has a hammer on one end with a starting position, and then the hammer is released. So the hammer goes down, and as it's going down, then it accelerates because of gravity, and then it strikes the sample, and the sample either deforms and doesn't fracture, or it fractures. So the test is performed on several samples, some of them with variations of this height. So this height here is varied, and some samples do not undergo fracture, but others will fracture, and therefore we could determine the critical height that causes fracture of the sample. So the critical height, let's call it H0, and the hammer is at this initial position, and then the hammer, as it is released, it is computed to have a velocity of 3.7 meters per second as it is striking the sample as a standard velocity. And once the sample breaks, then it absorbs a certain amount of energy. Then the hammer does not rise as high as the initial position, and it only rises up to a lower level. The difference between the initial and final position is delta H, and delta H corresponds to a potential energy that is absorbed by this sample. So the potential energy is the mass of the sample times the acceleration of gravity g times delta H. the result is in units, standard units of foot-pound. So there's a standardized unit here, and therefore we can study the influence of temperature and strain rate on various mechanical properties. So let's kind of go back to talk about the effects of strain rate or temperature on several mechanical properties. First one is impact, which we discussed right now. So the impact, we plot the impact energy, the Charpy energy versus the temperature. So the Charpy energy is in foot-pound. So you notice here for a steel, the Charpy energy is in fact very low at low values of temperatures, and then it rises sharply and it reaches a plateau. So it has one plateau at high temperatures and a lower shelf. So this plateau here is called the upper shelf. So this is the upper shelf. And this plateau here, it shows 0, but it's very, very small. This is called the lower shelf. So these are the different levels of impact energy that is absorbed by the material. And we notice that at very low temperatures, the impact energy absorbed is extremely small, maybe a few foot-pounds. And at high temperatures, above room temperature, the impact energy absorbed is quite substantial. It's on the order of 50 or 60 foot-pound. This is, I'm talking about steels, and in particular, these are ferritic steels, ferritic martensitic steels. Stainless steel does not undergo this transition from lower values to higher values. This transition is called the ductile to brittle transition. And in short, in the design world, this is called the DBTT, the ductile to brittle transition temperature. So there's a critical temperature below which the steel, the ferritic steel, is brittle, above which the ferritic steel is ductile. And this is standardized here to correspond to 30 foot-pounds. So at 30 foot-pound, here the critical temperature is nearly 0, but the DBTT, which is this temperature, depends basically on the type of steel and the alloying and so many other factors that must be considered. The next property, set of properties that I'd like to explain is the strength of the material, the yield strength, and also the ultimate strength of the material. How does the temperature affect these two properties, or the strain rate for that matter? So here in this graph, I have the strength, either the ultimate, this is the ultimate strength of material, or the yield strength of the material, and the yield is shown in red. So the ultimate is in blue and the yield is in red. And you could see that the dependence here is on the strain rate, epsilon dot. And epsilon dot is how fast we apply the load on the material. So if I have a material and I'm pulling, then the rate of motion of the top surface is delta L with this, by delta T, this rate of motion. If I divide this by L, that gives me d epsilon by dt, which is epsilon dot. So in standard mechanical tests, this rate is about 10 to the minus 3. In creep tests, this rate is about 10 to the minus 6. In high impact tests, like shock loading, for example, this rate can be above 10 to the power 3 or 10 to the power 4. If we have laser shock, for example, then we can achieve rates of 10 to the power 6 or 10 to the power 7, second minus 1. The unit is second minus 1. So as you can see that the strength depends on that rate. As the strain rate increases, then both the yield strength and the ultimate strength increases. This is the yield, and this is the ultimate. And the interesting aspect of this is that the rate of increase of the yield with respect to the strain rate is steeper than the rate of increase of the ultimate with respect to the strain rate. So the ratio of these two, the yield strength starts to approach the ultimate strength at very high strain rates, which means that between the yield and the ultimate is where there's work hardening. And as this window starts to close, this is a wide window, this is a window that indicates hardening. The window starts to decrease at high strain rates, which indicates that the material is basically brittle, and it will fracture once it just goes a little bit beyond the yield point. So at high strain rates, the material is brittle. At low temperature, the material is brittle, and one has to watch those effects on material properties. If I look at the total elongation, the total elongation does not change very much with the strain rate at high strain rates. The next effect of environmental variables is the effect of the temperature on the yield and on the ultimate strength. The yield, both the yield and the ultimate decrease as the temperature increases. So if you look at, for example, the ultimate strength of the material, you see that it increases slightly, and then it starts to decrease as the temperature increases. So for all practical purposes, we cannot really use steels above approximately 500 degrees centigrade. So this is 500 degrees centigrade, because the steel becomes very weak. The level of the strength of the steel is less than about 1/2 of the strength at room temperature. And therefore, at high temperature, we would have to watch for the yield, both the yield and the ultimate strength of the material decreasing precipitously to the point that the steel may have to be designed to carry very low loads at these high temperatures. And with that, we have reached the end of this segment on the mechanical behavior of materials. And thank you for watching, and I'll see you on my next video.